Good day to you. We're going to address a fundamental problem in thermodynamics today, one that was only solved a century ago by Albert Einstein, of all people. That is the problem of Brownian motion. Brownian motion is named after the Scottish botanist Robert Brown, who described it in 1827. In a nutshell, Brownian motion refers to the spontaneous jittery motion of tiny particles in a fluid. Brown wasn't the first to describe it. As far back as 60 BC, the Roman philosopher Lucretius described the dancing of dust particles in a beam of light. Why we call this Brownian motion rather than Lucretian motion was because Brown did an interesting experiment. Brown was observing pollen particles under the microscope and noticed that there were tiny particles within the pollen grains that exhibited a jittery motion. At that time, biologists were engaged in the search for some kind of vital stuff that animated matter. The question Brown sought to answer was whether the particles in the pollen grains were jittering because they were in something alive, or was it just something little things did, whether they were alive or not. So Brown took dust particles, watched them under the microscope, and found that they also jittered just like the particles inside the pollen grains did. So Brown concluded that the motion did not arise from some kind of vital stuff, but was a purely physical phenomenon, and that's why we call it Brownian motion. Albert Einstein solved the problem of Brownian motion only in 1905, and his solution connected it in a deep way with the problem of thermodynamic temperature and diffusion. And in doing so, he opened the door to some interesting biology as well. We're going to be looking at Brownian motion today using the particles that accumulate in little ponds of water like this. So let's scoop up some water and get started.
This is what Brownian motion looks like. The objects you see are tiny grains of dust and some larger particles. This view is magnified about 1200 times. As you can see, the motion is incessant and seemingly random. The explanation for this motion is fairly simple. The visible particles are bombarded on all sides by the smaller molecules of the water. The collisions transfer momentum from the molecules to the particle. When the distribution of collisions is uniform, the net transfers of momentum cancel and the particle doesn't move. At very small scale, there's a chance that the bombardments will not be uniformly distributed, and neither will net transfer momentum to the large particle. When this happens, the particle is jostled slightly, first one way, then the other. The net result is jostling motion of the visible particles, Brownian motion. Let's take a closer look at this jostling motion. How intense is it? We can quantify this. We'll zoom in on a small patch and track the movements of three particles, one large in the red circle, one medium in size here in the green circle, and one small outlined in the blue circle. There's a movement bias in all three. That's due to a slight flow of the liquid under the cover slip on the microscope slide. Aside from that, the movement for all three is first one way, then the other, sometimes forward, sometimes back. This is called a random walk. Let's look at the tracks of the random walks by themselves. This type of motion is characteristic of the movement of particles at very small scale, what is now called the nanoscale, slightly larger than the molecular scale. What is striking is the effect of size. The small particle has moved about twice the distance of the large one. This size bias has a statistical explanation. We can quantify the distance moved between each frame of the video. That's at intervals of about 1/30th of a second. Each bar represents the likelihood of a movement of that particular distance. This is the likelihood that a particle will jump less than 0.1, while this bar is the likelihood of a jump of less than 0.5 but greater than 0.4. Let's compare the small particle with a large particle. We can see why the small particle's random walk takes it further. It is more likely to make long jumps and less likely to make short jumps than the large particle is. We see the same thing, but less dramatically, comparing the medium particle with the large particle. The medium-sized particle is more likely to make longer jumps than the large particle. Indeed, the large particle shows no discernible movement in more than 50% of the frames. If temperature is random thermal motion, then temperature should also affect Brownian motion. Here are two clips showing Brownian motion at 25 degrees Celsius and at 8 degrees Celsius. It appears that the motion is less when it's cooler. We can quantify this. We can use image analysis to measure the total motion of a particle. Here, the light indicates motion. The brighter the light, the more intense the motion. The cool particle on top doesn't look much different from the warm particle below, but when we quantify it, we see that total motion is greater when it's warm than when it's cool, as we expect. We can also track how temperature affects the random walks. Here are tracks from 5 cool particles, and here are 5 tracks from 5 warm particles. It's obvious that random walks are longer when they are hotter. Let's measure the average distance traveled by the 5 particles over 5 seconds. Clearly, it's greater when the system is warmer. We see why when we look at the distance traveled every 0.2 seconds. When the system is warm, longer steps are more frequent than when it is cool. This makes sense. Temperature is essentially random thermal motion. Increase the temperature, and the thermal motion increases, and with it the Brownian motion as well. The statistical nature of Brownian motion connects it to another phenomenon, diffusion. Diffusion is a movement of a substance down a gradient in its concentration. Diffusion is pretty easy to demonstrate. We'll look at the diffusion of a dye, methyl green, under the cover slip of a microscope slide. We start with a drop of water and lay a cover slip over it to provide a thin film of water. We then take some methyl green on the end of a toothpick and spread it along one side of the cover slip. This provides a clean boundary of high concentration dye along the edge of the cover slip. We can follow diffusion by following the spread of the dye under the cover slip. Diffusion can move solutes very quickly over small distances, but it is very slow over long distances. You can see this in this 18-hour time-lapse video of the spread of dye under the cover slip. We can measure the rate of dye spread by looking at the rise of concentration at various points under the cover slip, at 3 millimeters from the edge, then also at 8, 12, 16, and 20 millimeters from the edge. These cover slips are 22 millimeters across. As the dye diffuses from left to right, the dye concentration increases at each point. To mark the times at each point, let's take the time it takes for the dye concentration to reach 50% of the maximum concentration. 3 millimeters from the edge, the dye shows up within a few minutes. However, it takes hours for the dye to move even a couple of centimeters across the slide. The connection of diffusion to Brownian motion works through something called the mean free path. This simply refers to the average distance a particle travels between collisions. A random walk is a sequence of free paths. The denser the particles, the shorter will be the mean free path. We can now see the connection of diffusion to Brownian motion. Suppose you have a concentration difference, as shown here at this boundary. To the right, the dye is concentrated, and to the left, it is dilute. The density of dye molecules to the right is higher than it is to the left, and mean free paths will be shorter there. Near the boundary, there will be a bias in the direction of mean free paths. To the left, where the density of particles is less, mean free path will be longer in that direction. To the right, particle density is greater, and mean free paths will be shorter in that direction. The net result will be a statistical movement of dye particles to the left, diffusion. This raises an interesting point about equilibrium and Brownian motion. If we look at a video clip of Brownian motion forward in time and compare it to the same clip running backwards, it's impossible to tell the one from the other. This is because this is a system at equilibrium. There might be molecular jostling, but it has no direction. If we look at diffusion of a dye, however, there's no question about which clip is running forward and which is running backward. This is because Brownian motion can take a system at disequilibrium and drive it toward equilibrium. In so doing, it does work, and this illustrates an important point about thermodynamics of life. Brownian motion works because of the random thermal motion of molecules. This motion represents energy. A moving molecule has a kinetic energy that is proportional to the square of its velocity. This raises a question: why can't this energy be tapped to do work? This is the rationale behind a supposed perpetual motion machine, the Brownian ratchet. The machine consists of several parts, all small enough to be moved by Brownian motion. There's a paddle that, when struck by molecules, can turn about an axis. This is attached by a drive chain to a cog. The cog can only move in one direction, its direction controlled by a pawl. As the cog turns, it can do work against a load. Here's how it supposedly works. Brownian motion of molecules bombards the paddle, exerting a force that will turn it clockwise at times and counterclockwise at others. The cog's counterclockwise movement is checked by the pawl. Clockwise motion requires sufficient energy to lift the pawl. Weak collisions with the paddle won't impart enough energy to do this, but there will always be a few collisions that can. When this happens, the cog advances and the machine does net work. There's no technical obstacle to building such machines. These nanomachines are etched into silicon chips using the same technology that makes microchips. There's even a ratchet. So what's holding us back? Will nanotechnology finally open the door to the elusive perpetual motion machine? The answer is no, and the reason is that there is no door to perpetual motion machines waiting to be opened. We only imagine the door exists because of flawed logic. If a machine is small enough to be moved by Brownian motion, then Brownian motion will affect all its parts, not just the ones we like. In our Brownian ratchet, this means the pawl will also be pummeled by Brownian motion. At times, these will be sufficiently energetic to lift the pawl. When this happens, the ratchet fails and the cog unwinds. Once again, the second law rears its head. There is no free lunch. This is not to say that Brownian systems cannot do work, just that it has to be paid for, and in the coin of the realm, by tapping gradients of potential energy. In the case of diffusion, the work of redistributing dye molecules was driven by gradients in concentration. High concentration is an unnatural state which it takes work to undo. Brownian motion does this work through biases in the mean free path of molecules, which ultimately restores a state of equilibrium, uniform distribution of dye. This is the problem for living systems. They must do useful work, creating order, but they must do so at a scale where Brownian motion is always acting to undo the effort. Here's an example. This is a tiny bead being walked along a microtubule by a motor protein called kinesin. This is clearly not a random walk, yet it operates at a scale where it should be. Kinesin is a so-called Brownian motor. It is like a Brownian ratchet, but now there's an energy gradient driving the system. Kinesin is a bipedal walking protein. It consists of 2 feet on the end of 2 long legs of protein. The feet bind reversibly with a microtubule. This cycle of binding and unbinding takes energy, which is supplied by ATP. The protein can walk because the energy released from the ATP at one foot changes the molecule shape in a way that ensures the alternate foot will always swing forward. As ATP now cycles through the alternate foot, the initial foot is now swung forward. The end result is an orderly progression of the kinesin forward.
All right, let's review what we've learned. We learned that Brownian motion is a statistical phenomenon resulting from the random collisions of atoms with larger particles. We also learned that at equilibrium, Brownian motion is time invariant. It looks the same going forward as it looks going backward. We also learned that Brownian motion can have directionality, but only when there is a larger disequilibrium involved. This is what drives the fundamental process of diffusion. Third, we saw that Brownian motion is driven by the thermodynamic temperature of a system. Because thermodynamic temperature comes from a system having some kind of inherent energy, this has led some to propose interesting devices known as Brownian motors, or Brownian ratchets, which could hypothetically serve as perpetual motion machines. These too fail to live up to their promise, although something like Brownian motors are common in living systems. Okay, that's all for now. Until we meet again, this is Scott Turner, wishing you a good day.